Hello there. You're very welcome to the lesson number 3 of the Dimensional Analysis chapter. I'm your own personal physics tutor, Dr. Rima McMullen. In this lesson, we're going to see how the dimensional analysis methods can help us determine the time period of a simple pendulum, the time period of a spring and a mass system, and the time period of a satellite that is going around its planet in a circular orbit. So, the problem number 1 is based on a simple pendulum. It says that the time period t of a simple pendulum depends on its length and the acceleration due to gravity g. We're asked to determine the dependence of t on L and g. So the question is, what is a simple pendulum? A simple pendulum is a mass that is attached to a string and it is anchored to some surface like this here, this surface. And this mass can oscillate sideways. So what I mean by that is, let me show it to you in action. Here is a mass that is attached to a string and it is anchored to a surface. Here's your surface. What is the length L? The length L is that of the string. And the mass of this object, let's call it as M. Now, what I'm going to do is, I am going to pull this mass to one side, here. So the mass came to this side. Next, what I'll do is, after I have pulled it over, so what I'm saying is, I have this mass that is attached to a string, okay? I am going to pull it to a side, like this. After this, I'm going to just let it go. I'm going to just release it. What will this mass do? It will come back to its original position, which is the equilibrium position. It's going to overshoot this equilibrium position and go to the other side. And then it will come back here, go to this side. It will stop here, turn around, come back to its equilibrium, overshoot, go to the other side, stop there, come back to equilibrium, overshoot this, go to the other side. So let me show this to you in action. Here. It is like grandfather's clock. So the system that I've made, it is kind of a rough approximation of a simple pendulum, but it shows the point. Anyway, back to this. So you start like this here. So back here, you pull it to one side, let it go, goes back to equilibrium, and overshoots the equilibrium, goes to the other side, and comes back. That was our simple pendulum. Hello. You're very welcome to the lesson number 3 of the Dimensional Analysis chapter. I am your own personal physics tutor, Dr. Rima McMullen. In this lesson, you're going to learn how dimensional analysis methods can help us determine the time period of a simple pendulum, the time period of a spring and a mass system, and the time period of a satellite that is going around its planet in a circular orbit. So moving on to problem number 1. We're told that the time period of a simple pendulum depends on its length L and the acceleration due to gravity g, and we are asked to determine the dependence of t on L and g. So the question is, what is a simple pendulum? So simple pendulum is nothing but a mass attached to a string, like this. So what you will do is, you will pull this mass to one side and then release it. So when you release it, what does this mass do? It goes back to its original equilibrium position and overshoots it, goes to the other side and stops there momentarily. And it turns its direction and comes back to the equilibrium and overshoots it, goes back over to the other side, stops there momentarily and comes back. So it oscillates sideways like this. So this is a simple pendulum, a mass attached to a string, and in an ideal case, the string will be massless. We're told that the time period, which is the time it takes so the time period, it's the time that the system will take to go from equilibrium to the one side, back to the equilibrium, to the other side, to back to the equilibrium. So here is 0, 1, 2, 3, 4. So there are 4 quarters. It comes back where it had started from. It's the time for one cycle. One cycle is start in the middle, go to one end, come back, go to the other side, come back. Or you could say that it starts at one extreme, goes to the equilibrium, goes over to the other side, comes back to the equilibrium, and comes back where it had started. That is one time period. We're told that this time period, it is proportional to the length L of the string and the acceleration due to gravity G. And we're asked to determine the dependence of T on L and G. That dependence will be these powers A and B. So we're basically asked to find these powers A and B. These powers tell you how T, the time period, it depends on the length L and the acceleration due to gravity G. Okay, now we have there the sign of proportionality. What you do is you take away the sign of proportionality and introduce a constant k of proportionality. And this constant k, it is dimensionless. It's a dimensionless constant of proportionality. All right, next what we're going to do is we're going to insert the dimensional formula for each of these factors in this equation. On the left-hand side, I have time period. Time period is M0, L0, T1. K is dimensionless on the right-hand side. Then we move over to L, and L is just the length. So you get M0, L1, T0. This is the dimensional formula for length L. And length L is raised to the power A. So here I have raised these parentheses to the power A. Next, I have acceleration due to gravity G. The dimensional formula for acceleration is m0 L1 t minus 2. And this is going to be raised to the power B. Now, if you do not know how I'm writing these dimensional formulae, I recommend that you watch video number 2. That means the lecture number 2 for dimensional analysis. In that lecture, I have shown you how to get these dimensional formulae and also what the dimensions mean. Okay, moving on. Next, what I'm going to do is I'm going to bring these powers, both of these powers, inside the parentheses here, like this. So when I bring A inside these first parentheses, what do I get? M to the power 0 times A is 0. L to the power 1 times A is A. T to the power 0 times A is 0. Now for the second set of parentheses, B is coming inside the parentheses. M to the power 0 times B is 0. L to the power 1 times B is B. T to the power minus 2 times B is minus 2B. And the left side we know is simply M0, L0, T1. On the right hand side, we're going to apply the basic rules of algebra. So m to the power 0 times m to the power 0 gives us m to the power 0 plus 0. Then I have L to the power A times L to the power B. Gives me L to the power this A plus B. Last I have L. L to the power, T to the power, let me use blue color there. T to the power 0 times T to the power minus B. This gives me T to the power 0 minus 2B. Let's close the parentheses. Equal sign in between. Next, what we're going to do is wherever we see the same factor here M. That's a factor on the left-hand side. And on the right side, I have this M. So equate these two. It's like saying if I have an equation x to the power 2n times y to the power 3m equals x to the power 6a times y to the power 0. Here you have this factor x to the power 2n on the left side and factor x to the power 6a on the right hand side. Now since these bases are same x, that means you're going to equate these factors. X to the power 2n on the left side equals x to the power 6a on the right side. Similarly, this factor over here, y to the power 3m on the left side and y to the power 0 on the right hand side. These are also equal here. Why? Because their bases are same. Now, whenever the bases are same, that means the powers are also same. So this equation implies that 2n equals 6a, and the bottom equation implies that 3m equals 0. So I'm going to apply the same logic over here now. And what that will give me is m to the power 0 on the left side equals m to the power 0 on the right side. Does that give me anything meaningful? Not really. So we don't need to even bother about that. However, L to the power 0 on the left side equals L to the power a plus b on the right hand side. This will give us something. So I'm going to write this down. Next, t to the power 1 on the left side equals t to the power minus 2b. 0 minus 2b is minus 2b on the right hand side. Now, for this top one, L is the base on both sides. So if the bases are same, that means powers are same. So 0 equals a plus b. Similarly, for the second one, 1 equals minus 2b. All I'm doing is equating the powers because the bases are same. Now, let me quickly rewrite these. 0 equals a plus b and 1 equals negative 2b. The second equation gives me b equals minus 1 half. If I insert that in the first equation, what does that give me? 0 equals a minus 1 half. Solve this and you will get a to be equal to 1 half. Okay, so I got my a to be 1 half and b to be minus 1 half. What was my equation? My equation was t equals k times L to the power a times g to the power b. And my goal was to determine a and b, which I have now. So t equals k times L to the power a, which is 1 half, times g to the power b, which is minus 1 half. How else can I write this? I can write this as k times L to the power 1 half over g to the power 1 half. And this is equal to k to the power square root of L over g. Now it turns out that this k is equal to 2 pi. And that is determined by doing experiments. So here is the formula for the time period of a simple pendulum. Let me box it in. Here we got it. The time period of a simple pendulum. So what we did was we started out with this dependence equation. T equals k times LA times GB. Then we wrote down the dimensional formula for each of these factors, except for k. Why? Because k is a dimensionless constant. Then we just carry out our math and solve for a and b, which finally gives us this equation. Now, is this the only way to do it? No. This is where we use the dimensional formulae. We could have used just the units to solve it, using just units. When would I use using units? Anytime I'm not asked to show using the dimensional formulae, or if I'm in a time crunch and I'm taking a test where the answer options are all multiple choice, then whichever method I use, it doesn't matter. So I know that t equals k times L to the power a times g to the power b. Again, my goal here is to solve for a and b. The SI unit for time is seconds. K is dimensionless. Dimensionless means unitless. Dimensionless implies unitless. Now just a side question here. A side question. Let's say a quantity has no units. Okay. Would it have dimensions? No. It means no dimensions. If it doesn't have any dimensions, it will have no units. If it has no units, that means it also doesn't have any dimensions. But is it possible that it does have units? Yes, there are units, but it doesn't have any dimensions. Yes, no dimensions. It's possible. There is such a quantity, angle. Angle has SI units of radians, but it has no dimensions. So this is one very, very important point that you should always remember, that angle does not have any dimensions. It will be handy many times. Okay, back to this equation for time period. We said that K, the constant of proportionality, does not have any units. So we're next going to move on to L. L is length. Its SI units are meters. M to the power A. G, the acceleration due to gravity, is in meters per second square. So meters per second square to the power B. This gives us second to the power 1 on the left hand side, meter to the power A on the right hand side, and this power B, it goes inside the parentheses and gives us meter to the power B divided by second to the power 2B. Okay, now here on the right hand side, since the base meter is same, that means we can add the powers A and B. That gives us meter to the power A plus B, and the second to the power 2B comes upstairs and becomes negative 2B. And on the left hand side I have S1, S to the power 1. Now let's do the same thing as we did before. We're going to equate the factors with the same base on each side. So on the left side, let's write meter to the power 0, because I have meter to the power something on the right hand side. Just so I could equate that factor with something, I'm writing meter to the power 0 on the left hand side. So that gives me now meter to the power 0 equals meter to the power A plus B. And seconds to the power 1 gives equals seconds to the power minus 2B on the right hand side. So the second equation gives me 1 equals minus 2B. Why? Because the base is same. When the base is same, you equate the powers. So this gives me, just like before, B equals minus 1/2. And this first equation gives me, since the base is same, equate the powers, you get 0 equals A plus B. And we know that B equals minus 1/2. Solve for A and you get 1/2. So just like before, we know that T equals K times L to the power A, G to the power B. Substitute these values of A and B, and you will get this to be K times L over G under the square root. Alrighty. In the second problem, we're told that the time period of a spring and box system depends on the spring constant K of the spring and the mass M attached to the spring. The spring constant is measured in the SI units. Using the techniques of the dimensional analysis, determine the dependence of time period T of the spring on K and M. Okay, so let's first understand what the time period of a spring and a box system means. So here you see this illustration where a box of mass M, the mass is M here, okay, I'll use a different color, is attached to a spring. Let's say you pull the mass over to one side. Let's pull it over to the right side, to this position over here. And then you let the mass go. What will the mass do? Would it just stay there? No. The spring that has been stretched now, you have stretched the spring, it wants to go back to its original position. So spring is going to pull the mass back toward this position. However, the spring is going to overshoot the equilibrium and come over here. And at this point, it will momentarily stop and the system will go back here. And again, it will overshoot and come back to this point. And it will oscillate back and forth indefinitely as long as the surface is frictionless. But we know that in reality, really, there's no system that is totally friction free. So let's see what the time period means here. And before we talk about the time period, instead of stretching the spring, instead of pulling the mass to the right side, we could have pushed this mass to the left. And when we do that, now the spring has compressed. When you let the mass go at this position, the spring wants to go back to its original position again. So it's going to go back here. However, it's going to overshoot. And now the mass will land here. The mass will stop momentarily here and come back. Okay. So the time that the spring and this box system takes to go from the equilibrium that is at rest to one extreme position, come back to the equilibrium, overshoot it, go to the other side, and come back to the equilibrium. So it starts here, goes over to the left, comes back to the right, goes all the way to the right, extreme position, and come back to the equilibrium. That is one cycle. But that is not the only representation of one cycle. I could have said that it starts over here at the stretched position, goes over to the other extreme, comes back. That is also one time period, one cycle. Or I could have said that it starts over here, goes over to the right, comes back over here. This is also one time period. Or you could say that it starts at the equilibrium, goes over to the right, comes back here, goes over to the left, comes back here. This is one representation. Or the other representation is it first goes to the left, then comes back to the right, and then goes back to the left to equilibrium. So all these are complete cycles here. And the time taken to complete one cycle is called as a time period. Okay, back to the problem. We're told that the time period depends on K and M. K is the spring constant of the spring. Spring constant tells you how rigid the spring is. The more rigid the spring is, that is, the more it wants to go back to its equilibrium position. The stiffer the spring is, the more the spring constant is. Okay. Now, spring constant K, it is measured in SI units of newtons per meter. We'll get to that. So time period, it depends on K to the power A and mass M to the power B. And we're asked to determine the value for A and B using the techniques of dimensional analysis. All right, we'll do that. First thing we're going to do is we're going to remove this symbol of proportionality. And when we do that, we introduce a constant of proportionality that I'm going to call uppercase C this time. Why? Because I do not want to confuse it with the spring constant K. All right, here we have K to the power A, M to the power B. Now this K, it is measured in newtons per meter. It is actually force divided by distance x. Okay, so the dimensional formula for force is m1, this is for force, m1 L1t minus 2. And we are dividing this by this x's, which is distances, dimensional formula, which is going to be m0 L1 T0. This will give us, okay, let me just very quickly rewrite it so I can show it to you in detail. So m to the power 1 divided by m to the power 0 gives you m to the power 1 minus 0. L to the power 1 divided by L to the power 1 gives you L to the power 1 minus 1. Last, T to the power minus 2 divided by 0 gives you L to the power minus 2 over minus 0. What does this give you? m to the power 1, L to the power 0, T to the power minus 2. So this here, okay, let me change this. This is not F anymore, just this top was F. Now this is the dimensional formula for K, the spring constant. Okay, my formula is T equals C, the constant of proportionality, that is dimensionless constant. It does not have any dimensions, that means it does not have any units either. K to the power A, M to the power B. Very well. Next, I'm going to plug in the dimensional formula for each of these quantities, which is T, K, and M. T is just time period. M to the power 0, L to the power 0, T to the power 1. C is dimensionless. We need not write it. K we just determined as M to the power 1, L to the power 0, T to the power minus 2. Then we have this to the power A. M, mass. M to the power 1, L to the power 0, T to the power 0, raised to the power B. Next, we are going to pull this A inside the parentheses. What does that give us? M to the power A, 1 times A is A. L to the power 0, T to the power minus 2 times A gives you minus 2A. Similarly, for the second dimensional formula, pull this B to be inside the parentheses. That will give you M to the power 1 times B is M to the power B. L to the power 0 times B is 0. T to the power 0 times B is still 0. On the left-hand side, I have M0, L0, T1. Okay, now on the right-hand side, wherever the base is same, since I'm multiplying these two dimensional formulae, wherever the base is same, we add the power. So M to the power A plus B. Then I have this L. Come on. L to the power 0. 0 plus 0 is 0. T to the power minus 2 plus 0 remains minus 2. Left side is M0, L0, T to the power 1. So just like we did in the first problem, wherever the base is same for a factor, we equate those factors. M to the power 0 equals M to the power A plus B. L to the power 0 equals L to the power 0. We can write this down, but really it doesn't give us anything meaningful. So might as well just not do it. Next we have T to the power 1 equals T to the power minus 2A. T to the power 1 equals T to the power minus 2A. Wherever the base is same, you equate the power. So 1 equals minus 2A. And from up here, 0 equals A plus B. The second equation gives us A equals minus 1/2. When we plug this A up here, this will give us B equals 1/2. So we just got A to be minus 1/2 and B to be 1/2. Okay. What was our equation? T equals C times K to the power A, M to the power B. M to the power B. Okay. And it turns out experimentally that C, the constant of proportionality, is again 2 pi. All right. Next, I'm going to put K to the power minus 1/2 times M to the power 1/2. This is our T. All right. T equals 2 pi times M to the power 1/2. Let's bring this K downstairs, and that changes its power into a positive power. What does that give me? 2 pi times M over K, this entire thing to the power 1/2, which is 2 pi times M over K to the power 1/2, which is square root. So here is the dimensional formula for here is the formula for time period of a spring and a box system. So yeah, sure, it was a little bit of work. It wasn't really too bad. But if you're not really asked to do it using dimensional analysis, you could have done it using just units, and that saves you a lot of time. So how do we solve the same problem using units? Let's use SI units. What's our equation? It is T equals C times K to the power A times M to the power B. Let's go ahead and plug in the SI units for each of these quantities here. Now we said that C, the constant of proportionality, is dimensionless, which means that it is also unitless. So we need not write anything for C. Well, it doesn't have any units to write. The SI unit for time period, T, is seconds. The SI unit for K is newtons per meter, and this is raised to the power A. The SI unit for mass is kilograms, and this is raised to the power B. Let's plug in an equal sign here. And let's raise the seconds to the power 1. Now, let's go ahead and bring this A inside the parentheses. What does that give us? Newtons to the power A over meters to the power A times kilograms to the power B, and on the left side I have seconds to the power 1. Now this Newton N, what is this? It is the SI unit of force. And from Newton's second law, force equals mass times acceleration. SI unit of force is newtons, SI unit of mass is kilograms, and SI unit of acceleration is meters per second squared. So what I'm going to do next is, instead of this Newton over here, I'm going to plug in the value for this here. I'm going to plug in kilograms times meters per second squared. Let's go ahead and do that. So instead of newtons, I'm saying it is kilograms times meters per second squared to the power A divided by meters to the power A times kilograms to the power B. Very well. Left side is still seconds to the power 1. Just like before, I'm going to bring this A inside the parentheses. What does that give me? Kilograms to the power A. Meters to the power A divided by seconds to the power 2 times A. This is going to be divided by this M to the power A times, we have this kilogram to the power B. Now this equal looks a little out of place, so I'm going to move it down here. What do I have on the left side? It's still seconds to the power 1. Now here, something very interesting happens, and that is going to be this meters to the power A cancels out this meters to the power A. Simple mathematics. This gives us kilograms to the power A divided by seconds to the power 2A times kilograms to the power B. Here, kilograms to the power B, kilograms to the power A, seconds to the power 2A. See that? Okay. Next, now at the top, I have kilogram to the power A times kilograms to the power B. Since the base is same, go ahead and add the powers together. That gives you kilograms to the power A plus B. And might as well just bring the seconds upstairs, which makes it seconds to the power minus 2A. On the left-hand side, I have seconds to the power 1. However, now on the right-hand side, I have this kilograms, but on the left-hand side, I do not have any kilograms. What if I write kilograms to the power 0? What is that? That is just 1. Why? Because any number raised to power 0 is 1. And multiplying by 1, we know changes nothing. Now we have this kilogram on the left-hand side, kilogram on the right-hand side. Let's equate these two. Kilograms to the power 0 equals kilograms to the power a plus b. Seconds to the power 1 equals seconds to the power minus 2a. Second equation gives 1 equals negative 2a, which will give us a equals minus 1/2. Plug that in here. Here, base is kilograms. Equate the powers. 0 equals a plus b. All right, so a plus b equals 0. Swapping left and right, no big deal. A equals minus 1/2 plus b equals 0. This gives b equals 1/2. Okay, so t is equal to c times k to the power a times m to the power b. C is 2 pi. We know it from experiments. A is minus 1/2, just like before, and b is 1/2. So that gives m over k under the square root is t. So look here. This is still a little bitty of work here. All of this is in units. And this was all in dimensional analysis. I prefer units unless I'm asked to use the dimensional analysis methods. Why? Because dimensional analysis take M, L, T, all of them. Here, I find it much easier. It's a matter of personal choice. You do it however you like to do it. Okay? All right, so that was the problem number 2, where we determined the time period of a spring and a mass system. Okay? After this, problem number 3, we are going to find out the time period of a satellite that is orbiting its planet in a circle. Let's go ahead and do that. So, in this problem, we're told that the time period of a satellite that is going around in a circular orbit around its planet depends on the radius of the satellite's orbit r, the mass of the planet mp, and the universal gravitational constant g. So g depends on the time period of the satellite, on the radius r. This is the radius of the orbit. mp, mass of the planet, and uppercase g, the universal gravitational constant. Now, be careful. Physics and chemistry are very case sensitive. You can't use uppercase g for lowercase g and vice versa. Why? Because lowercase g is the acceleration due to gravity, while uppercase g is the universal gravitational constant. Okay, now the problem is asking us to find out the dependence of t on r, mp, and g. So here it is r to the power a, mp to the power b, and g to the power c. So when we're asked to find this dependence of t on r, mp, and g, we want to find a, b, and c. Okay? Now, r we know has units of length or the dimensions of length. mp has dimensions of mass. But how about this g? Have you seen this before? Now, g comes from Newton's law of gravity. Have you heard of that? Definitely. Everybody who's studying physics, everybody who's has some kind of knowledge about anything has heard about Newton's law of gravity. So let's first figure out what the dimensions of this uppercase g are. Okay. To determine the dimensions of g, we're going to look at Newton's law of gravity. Newton's law of gravity says if you have two masses, m1, m2, whose center of masses are separated by distance r, then the force of gravity between these two masses, this is the force of gravity between masses m1 and m2, is directly proportional to the product of the two masses, and it is inversely proportional to the square of the distance between their center of masses. Now, just like before, when we take away this symbol of proportionality, we introduce a constant of proportionality. And this time that constant is going to be uppercase G. Now, so far in problem number 1 and 2, when we introduce the constant of proportionality in the case of simple pendulum and that of the spring and the box system, the constant of proportionality was dimensionless, but not over here. This G has dimensions. What are its dimensions? We're going to find out. So can you write G as, isolate G, can you show that G equals FR squared over M1 times M2? Let me know in the comments if you can do this. That will help me gauge what should be the level of these lectures and the problems that I'm making. Okay? So please do let me know if you can go from here to over here. Alrighty. Next, I'm going to now to write down next to get the dimensional formula for G, what I will do is I'm going to break down this force F into its components, which is going to be mass times acceleration. So this is mass times acceleration times r squared over m1, m2. Now, so far we have been writing the dimensional formula as mlt and their respective powers, right? I'm going to deviate from that a little bit just to make my life easy, okay? So what I'm going to do is, I have this m here, right? For this m, it is just m1, okay? Acceleration, here's my acceleration. Acceleration is, okay, I'm going to just write parentheses here. Acceleration is m0 l1 t minus 2. Any kind of m, l, or t, whichever of these has power of 0, I'm not going to write it, okay? So this is a is l to the power 1, t to the power minus 2. R squared, okay? R squared is going to be L squared. Very well. Divided by M1, this is M1, this is power, M to the power 1, times, here I have M2. And the dimensional formula of M2 will also be just M1. Okay, now let's go ahead and combine whatever can combine. M1, this cancels one of these M1s. Next, what I can do is I can bring this one upstairs. When it comes upstairs, it becomes m to the power minus 1. L. How many L's do I have here? L to the power 1 times L to the power 2 gives me L to the power 3. What else is there? T to the power minus 2. So here, this is the dimensional formula for G. Minus 1, 3, minus 2 are the dimensions of G. Okay, what do we have in the question? Coming back to the original problem. Here I had T was proportional to RA MPB GC. So RMG. T is proportional to R MP G. Powers A, B, C in order. Okay, cool. Take away this symbol of proportionality and introduce a constant K this time. Why? Because I do not have a spring constant like I had in the second problem. And the symbol for spring constant was lowercase k. So I didn't want to confuse two k's. That's why I used C, uppercase C, as the symbol for the constant of proportionality in problem number 2. But over here, it doesn't matter. And this k, constant of proportionality, is dimensionless. No dimensions. Just like before, we are going to now plug in the dimensions of each of these quantities. Let's start with T, M0, L0, and T1. All right, now tell me, what do I plug in for the dimensions of this K? It is dimensionless, so nothing. I mean, sure, you could say dimensions or the dimensional formula for K is M0, L0, T0. When this combines with anything, it really changes nothing. So there is no use of plugging it in here. It just wastes time and space. So Let's not do that. Let's be wise about what we do. R to the power A. M0, L1, T0. M to the power B. M1, L0, T0. And sure, I did have an power A here and power of B here. I'll be in big trouble if I forget those powers. G, M minus 1, L3, T minus 2 to the power C. Okay, now let's go ahead and combine this M. So M to the power 0, M to the power 1, M to the power minus 1. M to the power 0 times A is 0. M to the power 1 times B is B. M to the power minus 1 times C is minus C. Very well. L to the power 1 times A is A. L to the power 0 times B is 0. L to the power 3 times C is 3C. T. T to the power 0 times A is 0. 0 times B is again 0. Minus 2 times C is minus 2C here. All right. This gives us M to the power B minus C, L to the power A plus 3C, and T to the power minus 2C. Let's write down the formula on the right hand side. T to the power 1, L to the power 0, and I got here M to the power 0. Let's put these in parentheses. So I hope by now you know what I'm going to do next. Equate this. Equate these two. And lastly, T to the 1 equals T to the minus 2C. What does this give me? This gives me 1 equals minus 2C, which gives me C equals minus 1 half. From this equation, I get 0 equals A plus 3C. Now I know that C equals minus 1 half. That gives me A equals 3 halves. Okay. First equation, 0 equals B minus C. 0 equals, what is B? I do not know. I know C. B minus half. This minus half is for C. This will give you 0 equals B plus 1 half. Right? That will give you B equals minus 1 half. So what do we have? We get A is equal to 3 half, B equals minus 1 half, and C equals minus 1 half as well. What was our equation? It was T equals K times R, MP, and G, and the powers were A, B, and C. They were in alphabetical order. So what do we get? K happens to be 2 pi again, believe it or not. 2 pi. R to the power 3 half, MP to the power minus 1 half, and I have G to the power minus 1 half. That gives 2 pi times R cubed MP G and 1 half. Or I could say it is R cubed over MPG equals T. This is the time period of the satellite that is going around its planet in a circular orbit. So this was done using dimensional analysis. You want to do it using the units now? Let's go ahead and do it. Using units. T equals K times R, MP, G, A, B, C. Okay. Units of time period, seconds. units of K. What did we say were the dimensions of K? Dimensionless. Dimensionless means no units. Alrighty, so we don't need to write anything for K because, well, we don't have anything to write for K. It's units. R. Distance is in meters to the power A. MP. Mass. Kilograms to the power B. Now G. We said G was equal to force times R squared over M1, M2. Now, the units of G, let's be specific and say SI units of G are, what is the SI unit for force? Newtons. SI unit for R, meters. Well, R is squared, therefore meter is squared. SI unit for mass, kilograms. SI unit for the other mass, kilograms. Kilograms times kilograms is kilograms squared. Okay. Now newtons. Newtons equals kilograms times meters per second squared. Okay. So that's just for newtons. Times this meters squared over kilograms squared. Now, this kilogram cancels one of the kilograms at the bottom. What does this give us now? This kilograms goes upstairs and becomes kilograms minus 1, that is the power, times meters, meter squared gives you meter cubed. The second squared gives you second to the power minus 2. Now, that is minus 1, 3, minus 2. Now, we have already determined the dimensions of G right here. Minus 1, 3, minus 2 right here. So it's the same thing. So here, not much space to write here. I'm going to move this little bit over to the left. Time period is seconds to the power 1. K we said is unitless. R, meters to the power A. MP, kilograms to the power B. G, we said it is kilograms minus 1. Meters cubed, seconds minus 2 to the power C. Our goal is still the same. Figure out the values for A, B, and C. Alrighty? Let's see what we can do here now. Equals M to the power A, kilograms to the power B. Now bring this C inside the parentheses, okay? You will get kilograms to the power minus C, meters to the power 3C, seconds to the power minus 2C. Left-hand side is still seconds to the power 1. Okay. Now here, let's see what we can combine. Kilograms to the power B times kilograms to the power C gives me this thing. Kilograms to the power B minus C. So after mass, let's move on to distance, meters. Meters to the power A. And here's meters to the power 3C. First 3C. All right. Last I have seconds to the power minus 2C. Here on the left-hand side, I have seconds to the power 1, which is the, I want to use blue color here. For meters, what do I have on the left side? To the power 0. Kilograms, what do I have on the left side? Kilograms to the power 0. I'm writing this kilograms to the power 0, meters to the power 0 on the left-hand side, just so I could equate them, okay? And seconds, what does that mean? Just like before. Kilograms to the power 0 equals kilograms to the power B minus C. Meters to the power 0 equals meters to the power A plus 3C. Seconds to the power 1 equals seconds to the power minus 2C. Now from this, what do I get? 1 equals minus 2C. This one, I get 0 equals A plus 3C. First one, 0 equals B minus C. So just writing this down, swapping left and right, B minus C equals 0. A plus 3C equals 0. Minus 2C, okay, this is not my blue color. Minus 2C equals 1. So I'm going to solve this first. This gives me C equals minus 1/2. Very good. This middle equation gives me A plus 3 times minus 1/2 for C equals 0. This will give you A equals 3/2. Very good. Now I got A, B, and C, all three of them. A equals 3/2, B equals minus 1/2, and C equals minus 1/2. Let's go ahead and plug this value for C up here. B minus 1/2. Minus 1/2 is for C. Gives me B equal to minus 1/2. Plugging these values of A, B, and C in this equation for time period, which is T equals K times R to the power A, MP to the power B, and G to the power C. Plugging in the value of A, B, and C in this equation and K to be 2 pi, I get T equals 2 pi times R cubed over MP times G under the square root. Simple math. Let me know in the comments if you can do this thing. If not, I'll modify my lectures to incorporate teaching these things as well. So in this lecture, we have figured out time period of spring, simple pendulum, and a satellite. These are extremely important problems that are asked over and over in the competitive exams. So do not ignore these. These are important. If you did not know how to do these to begin with, watch these, it's okay. But then after watching it, pause the video and solve the problem on your own. See if you can do these problems on your own. Because honestly, you would not learn physics or math or chemistry or perhaps even biology just by listening to it or just by watching it. You don't learn it by watching other people do it. You learn it by doing it yourself. Okay? So solve these problems on your own. I'll meet you again in the lecture number 4, where we're going to solve several more problems on dimensional analysis. Until then, have a good one. See ya.